Hey class, what's up? Mr. Brotherton here, and we are going to be talking about the chemistry of life. Alright, I know when I was taking college biology for the first time, I was not excited to be starting with chemistry, but there's a couple really good reasons we need to start with chemistry. Alright, so biology reduces to chemistry, chemistry reduces to physics, our current state of understanding in physics reduces to really weird questions about determinism and all kinds of philosophical stuff that luckily we don't need to understand biology. Alright, but what we do need to understand is that at some point in time, chemical evolution gave way to biological evolution. So in chemistry, atoms can interact, they can self-assemble, they can make more complex molecules, and at some point those complex molecules assembled in such a way that we have the origins of life, and that's what we are going to be studying in this class, is life. Alright? Okay, so why are we studying chemistry? Let's start here. So the reason I have a picture of John Coltrane's Giant Steps is this is known as the most feared song in jazz. So I may appreciate this song from an emotional standpoint, but to truly understand this song, you have to have some understanding of music theory, right? So I can't appreciate it to the same degree that a jazz saxophonist can, or really anyone who understands music theory more than I do. So in order to understand biology, we need to understand the foundations, which are chemistry, because that'll give us a greater appreciation of all of the really cool and beautiful things we are going to be learning about. So chemistry is the foundation of biology, the same way that music theory is the foundation to understanding something as complex as John Coltrane's chord progressions in Giant Steps. So, first thing, everything is made of matter. What the heck is matter? It's just stuff that takes up space. So it has volume and it displaces space. Matter is going to be made up of atoms. And then atoms we can subdivide and be made of even smaller things like protons, which are going to have a positive charge. So here's our little proton. Electrons, or I guess neutrons, are going to have a neutral charge. So right here we have some neutrons. And then our electrons are going to have a negative charge. So right here we have an electron. So this is hydrogen because it has one proton, and here is oxygen because it has 8 protons. So different kinds of atoms equal different elements. We define atoms based on their number of protons. Alright, so right here, hydrogen, we know it's hydrogen. Why? Because it has one proton. Whereas we go over here to oxygen, we know it's oxygen. Why? Because it has 8 protons. So the really important ones in biology, you can memorize with the acronym CHNOPS. So carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The other ones that are also going to be important in biology are going to be sodium, potassium, magnesium, and calcium. Alright, so 25 elements are really essential for life on Earth as we know it. The big four, so 96% of everything you are is going to be made of carbon, hydrogen, nitrogen, and oxygen. The rest of you, about the other 4%, is going to be phosphorus, sulfur, calcium, and potassium, and we will understand why shortly enough. So the first thing we need to understand about atoms is they bond. They have different bonding properties. So if we look at our Bohr model here of this atom, its properties are going to be determined by these electrons in its outer shell. So really our whole entire world is governed by the outside of atoms, so the electron clouds of atoms just bumping into each other and interacting. So electrons basically determine everything we observe about atoms. And that's entirely dependent on the number of electrons in an atom's outermost shell. And we call that the valence shell. So this guy right here, this is going to be argon, all right? And you should hopefully remember from chemistry how something like argon or neon or helium are going to behave in our world. So let's talk about some more bonding properties. So electrons. like I said, the chemical behavior of all atoms is dependent on the number of electrons in the valence shell. So there is a magic number that all atoms want to get to, and that number is going to be 8. The reason for that, the reason they want to have 8 in their valence shell has to do with geometry, all right? It has to do with stability. So if they have 8 in their outer shell, they're significantly more stable, and that makes them happy. So they're less likely to be spinning out of control and acting crazy, basically. All right? So how's this thing over here going to behave versus how this guy over here is going to behave? Well, this one over here is going to be pretty hungry for electrons because it's a lot closer to having its valence shell filled. So it's going to be very, very hungry for electrons, whereas this dude over here, he might not care as much. He might be more willing to give up these 2 electrons because if you look here, the second shell already has 8. So this will be a much more stable configuration if this one can get rid of these 2, whereas this one will be much more stable if it can gain 2. So let's look at some elements and their valence shells. So if they are in the same row, then they have the same number of shells. So if you are in the first row, you have 1 shell. If you are in the second row, you're going to have 2 shells. Third row, 3 shells. It's pretty simple. The only thing you need to remember is that if you are in the first row here, this first electron shell actually only needs to have 2 electrons in it to be stable. After that, they all need 8 in them to be considered stable. So if you move from left to right, each element is going to have basically a sequential addition of electrons and protons. So the reason hydrogen has 1 electron here is because it has 1 proton. So that single positive charge is going to attract 1 electron to balance this guy out. All right, so the other thing you need to remember is elements in the same column are going to have very, very similar chemical properties. So all of these ones over here, these are known as the noble gases. We call them noble because they don't need any friends. They're above everyone else, okay? They don't need anyone. They don't need to bond with any other atoms because they already have perfect electron configurations. Now everyone else wants to be like them, okay? So here if we look at oxygen, sulfur, and fluorine and chlorine, these ones are going to be highly electronegative. That means they're going to really want to attract more electrons to them because they're really close to looking like neon. So oxygen and fluorine almost look like neon, and sulfur and chlorine almost look like argon. So they're really, really going to want electrons. Whereas if we look over here, hydrogen, lithium, sodium, and beryllium and magnesium, these ones are going to be a lot more likely to let go of electrons, okay, because then they'll have more stable configurations. What's interesting here is because they have the same outside number of electrons, so their valence shells look the same, they're going to have very similar properties. So beryllium and magnesium, even though they're different elements and they have different number of protons, but because their electrons kind of determine how they behave, because that's the part that's going to be bumping into other atoms, they actually behave very similarly. All right, so this is really important to remember. We'll get into this later. This is like some pretty deep chemistry for understanding biology, but basically what you need to understand is that oxygen and sulfur are the building blocks for life on our planet as far as energy exchange. We'll get into this a lot when we get into anaerobic respiration and cell respiration, but just to give you a little bit of a preview, most life is operating by actually moving electrons from one high energy molecule, say glucose, and actually removing electrons and transferring them to oxygen. So that release of energy is how they're going to power their bodies, okay? Some things do it a lot different. This might be an older form of respiration where they're actually going to be transferring electrons to sulfur. So theoretically, if life started around maybe like something known as a black smoker or a hydrothermal vent where there's a lot of sulfur, then early life would have actually been transferring those electrons to sulfur molecules and taking that energy and using it to power their cells. But we will really get into that later. Just a little preview. So atoms like I said, they really, really want stable configurations, and that is always going to drive all chemical reactions we're going to be talking about in this class. And because they want those stable configurations, one of the ways they can get them is by bonding to another atom. So the really important bonds in biology, the very weak bonds that do some pretty awesome things for us in biology. The first one's going to be a hydrogen bond. So that's just a simple attraction between a positive and a negative. And that's going to give us our hydrophobic and hydrophilic interactions, which we'll talk about in the next video. We also can get ionic bonds, so that's going to be a transfer of electrons between two atoms, and then ultimately we get really strong bonds, which are going to be covalent bonds, and that's the sharing of electrons. So right here, you have a hydrogen bond. What this is showing you is there is a weak attraction between your negatively charged oxygen here and your positively charged hydrogen. We'll talk about why that happens in the next video. And here you have a covalent bond where both of these hydrogens are sharing electrons because it makes them feel like they actually have two in their valence shell, so they're a lot more stable. All right, so why are covalent bonds really, really strong? Because you're actually sharing electrons. So they're linking together to share their electrons. So they're going to share them. They're both going to be holding on to the electrons, and it's going to form very, very strong molecules, like something like water, or over here we have H2. All right, so multiple covalent bonds. The more covalent bonds, the stronger your bonds are going to be, and the harder it's going to be able to break them. So you can have double bonds, like right here in the case of this double bonded oxygen. You can have triple bonds, which happens a lot with carbon, which is a very hard bond to break. It takes a lot of energy. So the more bonds you have, the stronger it's going to be. It's pretty simple. More is better. So right here you have methane, which is a hydrocarbon. We use that to power all kinds of things in our society, but all of those bonds potentially have a lot of energy that they can give us. So a nonpolar covalent bond, that means things are not going to be charged. An example, like I already showed you, was methane. So carbon is a really awesome, interesting element because it's very willing to both take electrons and share electrons. So it's not super greedy for electrons, which means that it's going to share them equally. Carbon's kind of a nice guy and is willing to share electrons with these hydrogens here. Therefore, no one ends up partially charged, so no one ends up holding the electrons for more of the time. They kind of share them equally. So very, very stable. And then we can end up with things like water. Water is going to unequally share our electrons. So the oxygen is very, very greedy. Okay, remember, it wants to look like neon. The oxygen is going to be super greedy. So more of the time, it's going to be taking those electrons from the hydrogen, which is going to give it a partially negative charge. And then our hydrogen is going to end up with a partially positive charge. So if you kind of look here, you can see this positively charged proton is going to be out here hanging out with no electrons surrounding it to balance it, so it's going to be partially positive. Whereas if you look here, the protons in our oxygen are going to be more surrounded by electrons, so it is going to become more negatively charged. And we call the tendency of an atom to attract electrons to itself its electronegativity. So if it's a hungry hippo for electrons, then it has a high electronegativity. So we call it polar because just like a magnet, it has two different poles, a positive pole and a negative pole. All right. Hydrogen bonds, that's a weak attraction between our charges. We're going to get into that in the next video, so I'm going to fly through it. And our last bond type here is ionic bonds. So if a covalent bond shares electrons, what happens in an ionic bond? Well, it makes ions, so it makes positively or negatively charged atoms. The reason for that is because if there's a vast difference between the two electronegativities of an atom, then one of them is just going to straight up steal the electrons, okay? So this guy over here, this chlorine atom, is going to be extremely greedy for electrons, whereas this sodium over here, if it just gets rid of one of these electrons, it's going to have a more stable configuration, so it's going to be more likely to give up its its electrons. All right. So that's a quick rundown of what's happening there. Hopefully that was helpful, guys. Stay curious. All right, bye.